In match problem 3, we have an office supply company that sells heavy-duty paper shredders at a price of P dollars per shredder. We're given a price-demand equation, and we want to answer what price should the company charge for markers. That should probably be for shredders. What price should they charge for shredders to maximize revenue, and what is the maximum revenue? So we are given this relationship between price and demand, but we're not given the function that we actually want to look at maximizing or minimizing. So the first thing we need to do is establish some function f of x, which is the function that we're actually interested in considering. In this case, we're looking at maximizing revenue. So what we want is the revenue equation r of x, which is always equal to price times demand, which in this case, our price is 300 minus x over 30. And demand is represented as x. So our revenue function is going to be 300x minus x squared over 30. The next step is to find the domain, which is again essentially our interval that we're considering this function over. So we want to find the domain of f of x. We can start off by realizing that our price point, whatever that is, has to be greater than or equal to 0, and demand has to be greater than or equal to 0. We're not going to have a negative demand. That would mean we're giving things back to people. We're not going to have a negative price. That would mean we're paying people to take our product. So price has to be greater than or equal to 0. Demand has to be greater than or equal to 0. So if our price has to be greater than or equal to 0, then our price-demand equation, 300 minus x over 30, also has to be greater than or equal to 0. That implies that negative x over 30 has to be greater than or equal to negative 300. And then multiplying both sides by negative 30 is going to flip the direction of that inequality. So we get x is less than or equal to 900. So starting off with this upper bound, or this lower bound for price, leads us to an upper bound for demand, meaning that our demand has to be bounded between 0 and 900. So now we can actually establish the problem. Which in this case, what we want to do is maximize the revenue function, r of x equals 300x minus x squared over 30. On the interval, 0 is less than or equal to x, is less than or equal to 900. So we haven't gotten into solving anything. Those initial steps were all just about setting up the problem so we know what it is we're actually trying to solve, what function we're trying to maximize or minimize. So the next step is to identify any and all critical values. So we take the derivative of our revenue function, which in this case will be 300 minus 2x over 30, or 300 minus x over 15. And we set that equal to 0, which will give us a result of x equals 4,500. So that is our lone critical value. And next we turn to the second derivative test. We first find the second derivative excuse me, of our revenue function. In this case, that's going to be 0 minus 1 over 15. So the derivative of our revenue function is negative 1/15. There is no x value there, so we don't even need to worry about substituting anything. The second derivative is always going to be less than 0. which implies that R of 4,500 is an absolute max. So our absolute maximum occurs when x equals 4,500. So now our last step is that we want to actually answer the questions that are being posed. So we have all of this mathematical information. Now we want to turn that into something that's more or less in plain English. So what we're saying is our absolute maximum occurs when x is 4,500. When x is equal to 4,500, then our value for p will be equal to 300 minus 4,500 over 30. So just going back to that price demand equation, which will be 150. And when x equals 4,500, not f, let's go with our revenue function. Our revenue function evaluated at 4,500 will give us 675,000. So we want to take this information and translate it into just a statement in plain English about what this means. So what we're saying is that our maximum revenue of $675,000 will be obtained when we're selling these shredders at a price of $150 per shredder. So what we found is the optimum selling price that will yield the maximum revenue. But to get there, what we actually looked at was the optimal demand. But again, in the end, we're translating this into a statement that's readable just in basic English so that someone else who didn't understand the mathematical work that went into arriving at the solution would not just be able to read this and know, perfect, we should charge $150 per shredder, and this is our expected revenue.